Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to talk about section 5.2 in our text. 5.2, and it's called Permutations. Permutations and cofactors. So that's what we're going to learn about. And actually, really, it's permutations and cofactors as they're related. So let's put in a little an implied as related to the determinant of some determinant of, we'll call it a sub n. So if n is 2, or we'll just put n as any counting number. So we'll start with a 2x2 matrix. Before we do that, let's take a look at the determinant of A, and there's a few properties we need to recall. So number one is that we said that the determinant of the identity matrix is very simply always 1. It doesn't matter, and that's for any identity matrix. Number two is this, and that is the determinant of the permutation matrix. Well, let's just do a P sub 2. Well, what that means is a permutation just takes the columns of the identity matrix and changes them around, or changes the rows. The result is the same. And so in other words, the only way you could change the 2x2 identity is in this way, 0, 1, 1, 0. Well, now let's not jump to the formula of AD minus BC, because that's what we're going to be deriving today. Instead, let's just take a look at what we know. Well, this is the same as if we make a row exchange. Well, each row exchange has a multiplication factor of -1 that we've seen. So this becomes -1, and now it just becomes the determinant of 1, 0, 0, 1. Well, that's just the determinant. That's -1 times the determinant of the identity, which is just -1 times 1. Okay, the next one that we need, 3, is the determinant of, I'm going to call it like a 2x2 diagonal matrix. In other words, it would look like something like this, A, 0, 0, D. Well, remember what we said. We said first the determinant is linear by rows. So I can factor in A out of the first row. So that would leave me with 1, 0, 0 times, and then a D. Not times, but just D. And then it's linear in the second row also. So now I have an A, and then times a D times 1, 0, 0, 1. Well, this is the result is just A times D times the determinant of the identity, and so that's just 1. So we have A times D. Our fourth piece that we need, number 4, our fourth piece is, recall this, the determinant, I'm going to put it of the determinant of S, and S is not symmetric. We'll call it the SI, and you know what, let's just write out the determinant of a singular matrix. So a singular matrix just has dependent columns. So it's of this form, maybe A, C, and 0, 0. You could put any multiple of A times C in here. I just multiplied by 0. Well, this is just, when you have a dependent column, this just becomes A times 0 minus C times 0. And so if you have a dependent matrix, our definition is that the determinant, or a singular matrix, the determinant of a singular matrix, or that is a matrix with dependent columns, the determinant is 0. Now, the next piece we need to know is, what is a permutation? So, a permutation is all possible orderings. Well, let's take a look. So I'm going to start with the most simple version would be, the second most, is a set. A set that has maybe the number, has the set 1 and a set the set of numbers 1 and 2. So if I want the permutation, so all permutations, and we write the permutations using, it looks like an ordered pair. Our permutations would be, well, you could have a 1 and then a 2. And your next one is you could put the 2 and then the 1. Well, that's it. That's all possible permutations of the set 1, 2. Well, what about the set 1, 2, 3? And let's write, again, all permutations. All permutations. Well, let's do this by design. So I'm going to start with the 1. And then I could put a 2 and then a 3. Well, that's the easiest of all of them. But now in order to keep track of these, we want to do this very carefully. So we're going to write this as 1. And then let's switch the 2 and 3. So 1, 3, 2. Okay, let's do this again. So the next one is, we've exhausted starting with 1. So now let's start with the 2. And then we'll go in ascending order. So 1, 3. My next permutation, again, we could start with the 2, but now we could switch the 1 and the 3. So 3, 1. And let's see, that's all the 2, starting with 2. So now if we start with 3, we could have 1, 2. And I could start with 3 again, but change the 1 and 2 to 2, and 1. And notice it looks like we have six permutations. And here's how you calculate the number. It's the number of elements in the set, n factorial. So n factorial means n times n minus 1 times n minus 2, all the way down to where you get to 1. And so in this first case, when we had a set of 2, there is 2 factorial permutations, which is 2 times 1, which is 2, which is what we saw. And for a set of 3 elements, we have 3 factorial. That's 3 times 2 times 1, which is also 6. So if I gave you a set of just 4 elements, there's going to be 4 factorial permutations. 4 times 3 times 2 times 1. Well, that's 24 different permutations. So you can see that the numbers grow quite quickly. Okay, now we're going to use this information and we are going to, and the properties, and we're going to develop the formula for a determinant of a 2x2 matrix. So I'm going to grab a fresh screen. And we're going to derive the general formula for it should be more clear, of the determinant of A2. Now we already know the answer, so let's tackle that without that insight. Here we go. So I'm going to start out with the determinant of A2. And now remember, it can be written, I'm going to write it out A, B, C, D, because it's just faster to write. Seems simpler, A, B, C, D. But I also want to remember this is the same as if I was to use the more formal subscripts of A11, A12, A21, A22. Okay, that would be the more correct way to be writing this. Now, get a prop here, fix my desk a bit. So now what we want to do is let's start, we're going to use the A, B, C, D form, and then we're going to end by going back. So what if we use linearity? Let's write this as the determinant of A plus 0, B plus 0. So we're just applying linearity to the first row. Well, that says that then I can write this as 2 determinants. One is going to be A and 0, and then CD. And then the second one is going to be plus, and now let's use the 0B and then CD. So that gave us these two determinants. Well, let's try this again. Let's try this again by using linearity in the second row. So let me write that out before we jump into it. So that means my second row will be C plus 0, D plus 0, A 0. And then we're going to apply that to the second determinant as well, C plus 0, D plus 0, 0, B. Equals, so now here we go. So I'm going to have this with A, 0. Then we're going to have a C, 0. Plus, then we're going to have A. The first row remains the same. And then we're going to have a 0, D. Plus, now then I'm going to have a 0B in the first row. And then I'm going to have a, let's see, we'll take the C, 0. Plus, now the other option is 0B, and then I have 0D. There we go. These are all four permutations, and we're going to see how this comes together in a moment. Notice this. We have to be really aware of what we're up to, because notice this. We have dependent, or let's call it, we have singular determinants, or singular determinants. I have it in this first matrix, in this first determinant right here, because I have a 0 column. And I have it again in this fourth determinant. I have a 0 column. So that's interesting. That just means that the determinant will come out of these middle two determinants. So let's just clear this up. So now I have that the determinant of A2 is equal to, I have the determinant of A0, 0D plus the determinant of 0B, sorry, 0BC, 0. Well, now let's apply all of our properties. The first one is that this first one, we can apply the property that this is just a diagonal matrix. Well, we already said that gives this just A times D. Plus, now this next one says that I could factor out the B and C. So this is going to be C times, we'll write it in alphabetical order, B times C. But then that leaves, just a sec, I have to sneeze. That leaves a 0, 1, 1, 0. Well, that's A times D plus B, C times the determinant of P. Well, in the 2 by 2 case, the determinant we said is just -1. So this is A, this is A times D plus B times C times -1. In other words, this is A times D minus BC. And that is where that formula comes from. But let's write it one more step. This is really A11 times D was in the 2, 2 position, minus, or actually let's write it this way, plus we had a determinant of P times B is the 2, 1 position. I'm sorry, no, it's the 1, 2 position. 1, 2 times the C, which is 2, 1. Now I want to look at this closely, because notice there was one more thing in there that we did very quickly, and that was what was the A11 A22? Well, it also had a determinant of a P, but its P was very simply the I, so there was no sign change. So plus determinant, oops. Let me clear that up. Let's write it a bit more clearly. So I had the determinant of I times A11, A22, plus the determinant of P times A1, 2, A2, 1. Well, this is just a sum. This is equal to the sum of the determinant of whatever specific P it is, whether it's I or a P that's important, or a P that changes rows, times, well, here's what we have that's careful. Notice that we need to be noting. First off, notice that the pattern here stays the same. First of all, we have the 1 and then the 2. Those are the rows. And here it is again, the row 1 and row 2. What changed? What changed, though? What changed is the second one. 1, 2. It changes, though, now to 2, 1. Well, 1, 2, 2, 1. Let me go back. 1, 2, 2, 1. Those, here it is. 1, 2, 2, 1. Those are the permutations of the columns. And that's the same permutation set that we looked at earlier. So let me go back. So when I come back to what I had, then this is, my yellow might get in the way here, the determinant of some P times A1, and what we call it is alpha. And then A2 times some value of beta. And that's it, where alpha and beta is the set of alpha and beta is all, let me write it this way, is all permutations. All permutations. So there we go. That is, and our author calls this, as a great title, calls this the big formula. The big formula. And that is the general form for a 2 by 2. Well, what if you wanted to extend that? Then the bigger formula, the AN formula, is this. The determinant of AN is the sum of the determinant of P times A1 alpha, A2 beta, times, and then you'd go all the way out to however many of these you have. The N may be N omega. And that would be where now we have the set of 1, oops, not 1, alpha, beta, all the way out to our omega. Those are all possible permutations. And that is the big formula for some n by n matrix. And in this next video, we are going to take a look at how that applies to a 3 by 3 and how that gives us what's called a cofactor matrix, which would give us the rest of the title to this video. Hope that helps. Thanks for watching.